Hello and welcome everybody to my second session of my lecture about statistical energy analysis and hybrid methods. This time we will talk about a system that some of you might not expect in the context of statistical energy analysis. We will talk about the damped harmonic oscillator as an example for the most simple linear system. For those of you who are familiar already with the harmonic oscillator, they can skip this lecture, but in terms of providing a self-consistent lecture, I would deal with some topics here in this chapter or session. That means talking about how energy is stored in resonant system, how power is introduced in such systems, depending on quantities like impedance or stiffness, dynamic impedance and stiffness, and so on and so on. And very important, and this is the clear link to SEA, I would show how energy is damped, how power is dissipated in such a system, and we will get some definitions that we will always use for the damping loss factor later on. Okay, so let's start. So the linear system damped harmonic oscillator is quite a simple system which consists of mass that is connected on a spring, could be fixed on a roof here for this example, and we have a damper. Mass m, vicious damping constant Cv, and Ks for the spring stiffness. The equation of motion for such a system is given by equation number 1, and such equations are solved by using a characteristic equation with the exponential function. If you do so, and entering this, we get rid of the derivatives, the time derivatives, and get the so-called characteristic equation. If we solve it, it is a quadratic equation. We get two solutions given by this expression here, and those two solutions converted into our ansatz will lead to this function, which is a combination, linear combination of the two solutions with some constants in the beginning. The result of those constants B1 and B2, they really depend on the initial conditions and on the criteria and the quality of the root solution that we will get. When the root becomes 0, we will just get one solution only, and this defines a new quantity which we call critical vicious damping. That's the damping which has exactly this value, and it's called, why it is called critical can be explained later when we come to the detailed solutions. In the next step, to clarify or to clean up the equation a little bit, we will perform some definitions of starting with the natural angular frequency, which is the ratio of stiffness and mass. So this defines the squared angular frequency, the so-called resonance frequency. If this is converted into the normal frequency domain, we have to divide it by 2 pi, this is the natural frequency. The critical vicious damping is also used to create new quantity that we call the vicious damping ratio, which represented by this quantity C, which is just the ratio of the vicious damping to this critical damping. And time period, which is the reciprocal of the natural frequency. When we use those constants in the equations 1 to 3, we will get a different form where we have, which is looking much easier, and the same is true for the solutions of the characteristic equation. And it becomes clear here the critical vicious damping is 1, and if this is 1 here, in this case, that means we will have a 0 root, and that means we will have exactly one solution. Good. Based on this description, we have three cases. The first one is that Xi is bigger than 1. This is the so-called overdamped case. But because we will get fully real solutions, we will have at 1, we have the famous critically damped case, and if Xi is smaller than 1, we will have a complex result for this characteristic constant, and this is what we call the underdamped case. Let's start with the not that much resonant case, which is the so-called overdamped oscillator. When we are entering both roots into equation 7, from 7 into 4, this gives a sum of decaying exponential functions, so not a real oscillation. And in the figure here, we have this giving this result with two expressions, B1 and B2. And if we enter the initial conditions like the elongation at time 0 or the velocity in x direction at time 0, we get for the two different values B1 and 2 the given expression here. A graphical expression shows what is the result of this. So this is the first term, which is related to the 0 time displacement, and we see the decay of this, but never reaching 0. This is why it's called the overdamped oscillator. And the second term here in this part, given by the green curve, this is going this. That's the green curve giving this expression. The combination of both, that means it's the overlay of this. And you see that it's even if we get a starting velocity to the 0 displacement, the mass never reaches the 0 position, at least not only in infinity. Good. Let's come to the critically damped oscillator case. This is where we just have only one sum. Due to this case, the result given by equation 4 does not fulfill all initial conditions. We need an extra solution, which is given by another b times t as an extra constant. If we introduce this in the initial conditions, we get the results for B3 and B4 as it is given here. Just to see, the critically damped oscillator reaches very fast the 0 condition. And just to compare it to a similar overdamped case, it would look like this. So this is the thing of the critical, that's a perfect damping that you can get. So the mass is really approaching the equilibrium status. Let's come to the case that is the most interesting one for our context, because we would like to have a resonance. That's the so-called underdamped oscillator. We get a complex root conjugates, and the solution of equation 7 looks like this. So we have a kind of global amplitude factor or whatever, which is also given here, which is representing the damping. We have a cosine function that's an oscillating one with a given phase factor, and in addition also some change in the resonance frequency. And that means we will finally have an oscillatory motion damped by this expression. And we see that the resonance frequency is not exactly omega 0, it's slightly lower due to damping effects. And this decreasing factor is what we call gamma here in this context. We can use also the solution to express this in amplitude and phase. If we do so, we would get exactly those two equations here below. Let's have a look at the one example solution. This would look exactly like this. So we have the starting displacement, the oscillator oscillates here, and the decay of the amplitude is given by this first term here in the equation represented by the dotted line. So that's a good example for the underdamped oscillator. This decay can be expressed in some kind of called decay rate given by beta tau. It's also related to the decay time, and that's the reciprocal of it. And if you just That's the time interval where the amplitude decreases to 1 divided by E, and those are the definition of the decay time, decay rate, and the relationship to our equation, which is here this C times omega 0, given here in this expression. Okay, so far for the damped harmonic oscillator without any external excitation. If we apply in addition a force, harmonic force that is exciting our oscillator, we have to write a new equation of motion or differential equation, and this is again the equation of motion of the harmonic oscillator excited by a force given by a cosine function. There's something missing here. There should be an additional phase if we would like to have the flexibility to put some phase factor into it, and this is a term that is missing here. Good. However, this is the right moment to introduce a complex algebra. So why is that? So this excitation, which is given by an amplitude, a frequency plus an extra phase factor, can be presented in a very easy way using a complex force vector times the e omega exponential function with the j omega t term as time dependency. We have to take the real value so that this is really equal. Please note that normally this real stuff is very often omitted and we are just using the complex algebra, but please always keep in mind that there must be the real value of it in the final realistic and real solution. So as mentioned, this is a complex force amplitude. The real is omitted, and the same can be done for the displacement, which is written in this form, and the velocity follows quite easily out of this displacement. The derivative corresponds to multiply the same thing by j omega, and then we get the complex velocity. It's worth mentioning that why I was insisting so much on the time convention when I introduced my convention. If we would have used a minus time convention here, we would have a minus everywhere here. So all the following formulas have a different sign. And this is why it's so important to understand or to know, at least for every textbook, what the time convention that's finally used in the book. Again, I used the plus version, so not the negative here, so we can stay with all the rest. Good. If we enter this ansatz into our equation here on top, we get again rid of our derivative due to complex algebra, and we have just the displacement, complex displacement and a force, and if we solve this for the force, for the displacement, we get this equation as the result or the displacement of the harmonic oscillator, which is excited by a complex force vector. So quite a simple formula, quite an easy solution using this complex notation. So let's have a look at the frequency response. Again, we can use magnitude and phase of the displacement, and if we do write the amplitude factor, it would get this value, and the phase would get this value. Please note that this is always the tangent of the relationship between the damping part and at the same time of the stiffness and mass part in the equation. And the same is true for the amplitude. We see here an expression that relates stiffness and mass with a certain resonance effect, and we have the additional damping effect, which is given by the second part. To write this in a good form, we use the static displacement as normalization. So the static displacement at frequency 0 corresponds, that's logic because that's only a static force acting at a spring. It's just exactly this 0 displacement equation. If we do so, we get the normalized amplitude and phase, and we get this expression here and this phase, and this is printed in those diagrams. We see, if we look at the amplitude, we see that it is infinite if there's no damping, obviously. If we introduce small damping, it's getting lower and lower. If we have, for instance, the critical case at 0, 1, we see that there's no oscillation at all, and this is getting worse if we have a high damping or C that would correspond to the overdamped case. Again, only for quite small damping values we will have a reasonable oscillation. Even for values around half, we cannot really identify the oscillation. Please note that the frequency is getting lower and lower the higher damping is, as mentioned in the formula. And the same is true for the phase. It's nearly a rectangular shape with no damping, but the phase is getting flatter and flatter depending on the critical, on the vicious damping ratio. Good. The maximum occurs at another frequency as mentioned here, so this is given by this equation. By the way, this is not the same as the decrease of the damped harmonic oscillator frequency. This is even another frequency because there's a 2. That was it was another expression. And the maximum value in the corresponding phase is given by this equation, and the phase at that point is given by this equation. Good. Now we come, the first step into our world of energy, power, and impedance is to have a look at the energy of our oscillator. We have two components of the energy, which is kinetic and potential energy, written by this equation. If we go through the math, we end up with a constant energy value, which that depends on the maximum displacement by this equation. What you can see here in the energy diagram, the total energy is given by the green line, and we see that the kinetic and the potential energy is exchanging energy. So either it's totally potential energy, and then it's 0 again, or it's total kinetic energy. But that's the classical effect of an oscillating phenomena. Good. Just note that this exchange takes place twice over one period. And this oscillation gives us shows that we need some kind of time averaging if we would have a look at the energy or the amplitude quantities of our signal. So we introduce the mean square value, which is this one. So this is just the average square value of our whatever given signal. It could be displacement or pressure. And if we take the root out of it, it's the so-called root mean square value, which is the root of our mean square value. When we apply this to our sinusoidal shape of displacement, here taking the cosine function, we see that the relationship to the amplitude is that we have to divide it by square root of 2 to get the root mean square value, and by a factor of half if we're interested in the mean square or in the square root mean square value. Good. So far for time averaging and energy in our oscillator. And now we move to some very important definitions and symbols. So we have, in our expression, we have forces, we have displacement and velocities. And the relationship or the ratio of such quantities leads to specific, let's say, dynamic quantities that are of great relevance in the further consideration. They are dynamic constants, and they are usually complex, given by the italic and bold figure scheme. We start with the dynamic stiffness. It's the ratio of force per displacement, and the reciprocal is the mechanical receptance. Often we rely on the velocity, and in this case we call it the impedance, which is the mechanical impedance with the force divided by the velocity, and the reciprocal of the impedance is called the mobility. Why do we need it? Knowing the shape and form of the mobility or the impedance gives us a hint of the nature of our dynamic system. So if we have a look at the solution of the damped harmonic oscillator, we just take our displacement solution and make a velocity using the j omega term again, and we get this as the impedance equation. So we have our critical or vicious damping plus a pure complex value, which is a kind of term that depends on the stiffness and the mass with different relationship of omega. So we see for high frequencies this one, the mass term is more important, and for lower frequency the stiffness term will become much more important. And this is what you get if we write the absolute value of the impedance. And here you can see that in the lower area, this term is dominating the impedance, and the high frequency, this term is dominating the impedance. And in the intermediate region, it is damping controlled. So this will become 0, so you can forget it, and only CV will dominate our impedance, showing a clear, a real value. This is why the argue will get 0. So from the phase, from the argument result, and from the shape, we know if it's more stiffness behavior, if it's more acting like a mass, or if we have a resonance occurring there. The real imaginary parts of the impedance have specific names. We call it resistance and reactance for the real and complex part, and for the impedance. And for the mobility, we say this is the conductance, and the complex part is the susceptance. There are also some expressions for the dynamic stiffness, but this would complicate things too much, so I will just use, because that's very often used in the literature, I will use the complex numbers and figures for mobility and impedance. Good. Now we have a look at the power balance. And for doing so, we take our equation of motion and multiply it by the velocity, here written as the derivative, time derivative of the displacement. And this would give to this strange form that can be, and here the first and third, this term and this term can be integrated and can be formulated as we can put the time derivative in front of this brackets and have here the pure vicious term. So we know that this is the total energy, and that's constant. That means this is 0, because the time derivative of this will be 0. So we will only have those remaining parts, and these remaining parts are a kind of power balance. Power balance of the dissipated power here, given by this term, and by the introduced power, which is given by this term here. And this is a kind of first mini SEA, because it's just giving us a power balance. So a power introduced in our system and the power dissipated in our system. The fluctuating harmonic motion is there, but it will not affect the total power balance of our simple resonator system. So what is the power that we really introduced into our system? How can we calculate it? The power is given by the force times the velocity, and we will again use the complex standards or complex mathematics to calculate it. Again, we need, in here we really have to use the real value, because otherwise we are completely lost, and it would be very dangerous to skip the real expression in this derivation. So we do this step by step and going through the mathematics. So here the real value is represented by this typical trick to get the real value out of a complex number, and take the real value, and it's not necessary, but that's definitely not a mistake. And we do the same for the velocity. And going through the mathematics, we will finally get an expression which gives us the real value of this term here, the red one, and this is the so-called constant active power. So this is where power is really introduced into the system. And the second, in this light green, and this is a reactive part. This is just oscillating. So it means here we will get a net power flow into our equation, and this will be reactive. So we introduce power into our system, but we also get the power back in the next half cycle. And this will become clear if we just make the average over one period. So this one here is existing, but it will vanish over one period. It will to a net zero power flow, but this will stay, and we will just get the remaining part for power flow. So, and now it becomes obvious why it makes sense to introduce quantities like impedance and mobility. Because in this equation, we can now express the velocity by using the other quantities. And if we do so, we will just have a squared force and the real part of the impedance, or the reciprocal of the impedance, or directly the real part of the mobility. And especially now it becomes clear why it's so important to introduce different expressions for the real and imaginary part of those quantities, because if you go back to the mobility a little bit, we call the real part conductance and the acceptance. We rely here on the conductance, and then we see that it is the conductance that is only relevant for the net power flow into our system. And the same would be true for the impedance. In this case, it would be the resistivity. Good. Now, damping. So until now we talked about vicious damping, but this is rare in real systems, because normally the damping is not proportional to velocity. There are many other options. It could be structural or hysteretic damping. It could be Coulomb dry friction damping. Another example is velocity squared or aerodynamic drag damping. And all those examples are examples for things that are non-vicious damping. To relate all the different damping phenomena, it's good to introduce the so-called equivalent vicious damping. And the idea is that we just consider the energy that's lost in a typical period cycle due to vicious damping, which is given by this term. And if we do go through the mathematics, we will have a vicious damping that corresponds to this value. So pi, vicious damping, omega, and the amplitude squared. And whatever other damping phenomena we have, this is what we call then the critical vicious equivalent damping, we will just relate it. So that means we take the same energy lost, but now we use the vicious equivalent damping, and this leads us to the definition. So we just identify the energy lost in the oscillator for whatever kind of damping we have, divided by those quantities, so p, omega, and the squared amplitude. So now we will go step by step and introduce more and more quantities, criteria, and figures for different damping identification. And we start with the quality factor for systems with small damping. In many practical applications, this vicious damping ratio is quite small. That means we can approximate our maximum displacement by a much easier question. So we will just not considering this again, because that's small and it's a squared figure. This will give us this approximation, and this will lead to a much easier expression for the phase value also. So it's just dependent on the vicious damping ratio. So amplitude and phase, so that means that, but again, this also means that the amplitude and the phase resonance are now occurring at the same time. And this magnification factor, so that means the result at the resonance with compared to the static displacement, this is what we call the quality factor. In fact, this is exactly the height of this peak, and it's called quality factor because the higher the peak is, the better the resonance, the better the quality of the resonator. And the relationship of this, if we just identify here using the above expression, is the relationship of the quality factor to our vicious damping ratio is given by this equation. Yeah, this is just repeating what I've said. Another option in such diagram, and this is really used in tests, is to check, to determine the bandwidth, the so-called half power bandwidth. That means we just take the displacement divided by a factor of square root of 2 and see what is the distance between this and this point. This is what we call delta omega, or omega 2 minus omega 1. And this is another option. We can go through the solution, because we know when we have this factor here, if we use this equation again, and if we do so, we get the relationship between the two different deltas of the delta omega, which is given by this equation. So we can, just by measuring the broadness of the peak or the bandwidth more or less, we can directly identify the critical vicious damping ratio, or which is the same, we can identify or calculate the quality factor of our resonator. Just one remark, you really need a resonance here. Very often such a diagram is used for determining the damping, but at the same time people forget that this is an approximation, because if damping is getting higher, this approximation cannot be used, and all the equations that you see here are no longer valid. So please keep in mind, for high damping, on about 10, 20, 25%, this will not work. However, it's used very often in practice. Good. Oh, there was something missing? No, that's fine. Good. So now let's come to some specific examples of damping. So one is so-called hysteretic damping, and here we say that the dissipated energy per cycle is proportional to the squared displacement amplitude. So the energy that would be equal to our, this is the delta energy that we are losing for every period, depending on the amplitude, by this alpha constant. And if we use our definition of the equivalent vicious damping, we will get this result. And we can enter this into our equation of motion. So again, just remember, this is the part where we are entering this. And we can rewrite everything which lead to a different form of our equation of motion. And the trick is now here that we are losing the velocity dependence, so that we just have omega squared value or displacement without any complex part. And that means it could be added to the stiffness constant, which is given by this loss factor that we have introducing here, and the value of the loss factor is given by this. That means we can introduce a kind of complex stiffness, which is a combination of the real stiffness factor of the spring plus the complex term given by the loss factor. Okay, using all this, our frequency response also looks differently. We can write this in this form again. We have not this complicated relationship. We just have the usual form, and we have here the damping loss factor, which is adding to the resonant frequency. Using this notation, again, please keep in mind that this kind of damping does not change the frequency. And this makes also the solution much easier than in the vicious damping case. And those are the relationship for the normalized amplitude and the phase, given by those expressions. And again, amplitude and phase resonance here this is not an approximation, this is coming with the assumption of the damping phenomena, they occur at the same frequency. The reciprocal at the resonance again is given by this equation, and we can find a good and easy relationship to the quality factor. So, and then we have also automatically created the relationship to our resonance, to damping loss, which is corresponding to the twice the critical vicious damping ratio, or is just the reciprocal of the quality factor. So the zoo of damping constants is getting more and more complicated. However, again, the dissipated power is given by this exactly the loss of energy over one period, which is one cycle. And if we express T in terms of omega, we can write it in this way. That gives us, and entering this again into this equation, that gives us this formula, which could be then at the end of the day converted into this expression. So the dissipated power is a damping loss factor times the angular frequency times the energy. And this is a very important equation because this is the energy loss, how we would describe it later in our SEA subsystem. On top, and this is a good example of, let's say, explanation and definition for the damping loss factor. The damping loss factor is defined by the lost energy divided by the total energy divided by 2 pi. So that's a good definition to understand what is our damping loss factor that can be used even to extend it to other damping phenomena. Okay, good. Again, the zoo of damping parameters. This is just a table that relates all the different quantities that we have. There are even more. There are reverberation time and so on and so on. But just based on the consideration taken here, we just have 4 quantities, or no, 1, 2, 3, 4, 6 quantities and how they are interrelated. And believe me, this is very important because so many software, whatever, they all rely on different definition of the quantities. Again, also consider some of the assumptions and formulas given here. Assume that you have quite a low damping, so they are not everywhere valid. Okay, good. Conclusions. That's so far for our linear systems and harmonic oscillator and damping chapter. Every resonator has a natural mode of vibration, a so-called resonance, at one specific frequency, and we call this the resonance frequency. The power input due to, for instance, an external force excitation is determined by the real part of the mechanical impedance or conductance. The imaginary part is just reactive. So whatever is given there leads to energy that's transported back and forth. Beside the resonance frequency, the power input is quite low because we just have the reactive part then. So that means we need the resonance and we have to excite near the resonance to introduce energy into our harmonic oscillator, which, you know this from bridges, could lead to a resonance catastrophe. Again, what I said, input occurs near the resonance frequency. And the damping results in energy loss and is a complex phenomenon that cannot be described. It can be described by many parameters. And the most important of all those parameters that I've shown you before, especially in the SEA context, is the damping loss factor. So this is something that you really have to keep in mind. Yeah, and that's it from my side for this lecture. Just one final note regarding damping. I mentioned very often that it is not easy to replace any prototype by models. Especially damping might be a very important factor of your modeling, of your simulation, but the only way to access it is to measure it. So you have no other option to determine, to get a realistic value for damping in your subsystem. And the same is true for all your let's say prediction of interior noise and vibration. So thank you very much for attendance and listening to my very short session on the harmonic oscillator. And I'm looking forward to seeing you again when it comes to more complex multiple degree of freedom system, but also linear. So goodbye.